talk about my research, the start with title testing drones. So, give you context. All of us know about cyber-physical systems. They have a very wide range of application areas, from self-driving cars, drones, industrial robotics, even satellites classified as kind of cyber-physical systems. The thing is that in this kind of systems, we have software, we have actuators and sensors that gather data from the environment and act on the environment and manipulate the environment. And with the advancements in machine learning and AI, they are getting more and more intelligent and more autonomous. Specifically about drones and for unmanned aerial vehicles, UAVs, they are being used in many different contexts, from monitoring construction sites to delivery to mapping to agriculture, helping in disaster areas like fires, and also cinematography and used in movie productions. They have different kind of physical devices like rotors, motors, and camera or sensors, camera or accelerometer, and this makes them pretty sophisticated in terms of testing. To give you a more detail on the architecture of this kind of system, this is not specifically about drones. This is called a robotic cycle. So the cyber-physical system or the robot interacts with the environment. So it gathers data from the environment through its sensors. The data comes to sensors, and then it's passed to the software part, which can be classified into 3 levels. The perception part that deals with dealing the data that comes from the environment, mapping or estimating the state of the system, and then planning the next actions of the system to reach its goals. And the control part that deals with controlling the actuators in terms of in drones, it would be controlling the motors, so the maneuvers and the movement of the drone is as we expect. And then this controls the actuators, and then the effect gets back to the environment. So the drone moves, and we have the next loop of this whole process, and we have new data from the environment. So, of course, the environment could be the real environment that drone will interact with, but we also have the simulated versions, so it helps with the development and testing phase. And there are many different simulators available as open source or as commercial software. Gazebo is one of them that I will focus more during this presentation. About the hardware, there are many different hardware available. Mechanical parts, electronic parts, and also full assembled drone that could be used right away and out of the box. Because there are many different manufacturers and many different kind of mechanical and electronic parts, it's hard to develop software that really can interact with many of different configurations of them. So there have been developments also in software part. There are 2 very popular software platforms for drones, and also they can also be used in other kind of robotic systems. PX4 and Autopilot both have a very strong community in GitHub, and they are very configurable, so they can support different kinds of drones, different kinds of motors, different sensors, and so on. But this also makes it a bit more complicated for us as software developers to be able to test, or first develop and then test our system. So how cyber-physical systems in general and drones in particular are tested right now is the de facto standard now is field testing. So you develop the code, develop the firmware or develop the software, and then you go to the field, put it on the real drone, and try to fly it. So this is, of course, reliable. You can be sure that the behavior that you see in the test is similar to what you will have in the production and in the real environment that the drone will interact with. But this is not something that you could reproduce, because there are many different environment factors, and each time you do it, these factors could be different, so they are not easily reproducible. You cannot really do in many different scenarios with the test with different conditions, so to be able to guarantee some kind of reliability or safety of your whole system. They're expensive. They need a lot of manual work and time-consuming, and also this could be unsafe both for the people who do it and for the devices that are being used in the test. So simulation-based testing is an alternative that are used for this task. Of course, simulation is reproducible, is scalable. We can even automate it in a DevOps pipeline. And in comparison with the field test, it's much more affordable, and it could be it's definitely safe. But the question is it really reliable? So if we test a drone in simulation and everything goes well, can we really guarantee that the same kind of situation could go the same way if we go to the real world? And in particular, is the software that we are using, we deployed on the simulated version of the drone, is it getting realistic inputs so we can expect the same outputs from it? And then can we expect the same behavior of the drone when we go to the real world? This is something that I try to experiment myself. So in the lab, we have a drone based on PX4, and I took it and I went outside and I tried to run it manually with the remote controller and do some simple flight and maneuvers. And I got this trajectory from the test that I did. Then, since PX4 logs almost everything that is done during any test, I took the log, I extracted the commands that PX4 received during my manual test, and I automated sending exact same commands at exact same timestamps to the simulated version of the drone. And you see that the trajectory that I got was not really that similar to the one that I got from the field. So given the same external commands, the simulated version of the drone didn't really behave exactly the same. And this could be due to differences in many things, like the simulated drone characteristics are different from the real one, the weight is different, the motor power is different, or the environment could be different. I could have some wind in the real world that I didn't have in the simulation, and so on. This is a very known phenomenon when we deal with simulators. There's always a reality gap between simulation environment and the real world. And this can be defined as the extent to which we can rely on simulations to faithfully mirror the performance of the cyber-physical system, in this case, the drone, from the real world. So this could even be quantified with some distance measures or similarity measures that we could define. So we took the differences between the two trajectories with the metric that I will show you later, and we got some pretty high differences between the two trajectories. So the literature here is not really much in terms of the testing of the software. There has been a couple of surveys with the industry, robotic and drone practitioners to see what is the state of the testing in those companies or in those industry partners. And they identify reality gap in the simulation, which I talked about, as one of the biggest obstacles of testing this kind of systems. And also, if they have some bugs and they want to debug it, it's really hard to reproduce those bugs that they have from the real environment in the simulation, so they can debug and then can maintain, or they can improve the quality of their system. There have been some research on sim to real transfer for robotic agents. This is a pretty different area, but close. So the idea here is to train some robotic agents in simulation and be able to move them into real world with minimum additional training or minimum effort or a minimum loss of performance. So the idea here is to complement the simulations that we have done during the training in simulation with some small portion of real-world observations to complete the training of these kind of agents in the real world. But this is not something that we could also use when we talk about testing. There have been some recent work on augmented reality for testing cyber-physical systems or drones. This is an interesting direction which combines the data that comes from the real world with the data that comes from the simulation environment. So we have two modules that interact with the real world and also with the simulation environment. We mix the sensor information from these two worlds, and then we give the software this kind of mixed reality. So, for example, the camera images could come from the real world, but the other data could come from the simulation. So we can somehow test in a mixed kind of reality situation. But something that we saw is missing here is to generate realistic simulation-based tests. So the thing is that there are some works that generate simulation-based tests for different kinds of cyber-physical system. There are a lot for self-driving cars, but they are, to some extent, we could say that they are artificial. They are not something that could be really happening in the real world. So what we wanted to do is to get data from a real world test and try to replicate it in the simulation environment. This work is the approach that we came up with, called it Surreal, testing UAVs in the neighborhood of real flights. This is a joint work with Sebastiano from Zurich University of Applied Sciences and Paolo. And we recently submitted this to ICST, and we're waiting for the response. So the idea here is that, as we see before, simply replaying some external commands in simulation could not faithfully replicate the field test. And because of this, this will not leverage the software of the drone also in the same way in the simulation, and the inputs to this software are not realistic. Our goal is to first systematically replicate field testing simulation. This would be according to some specific logged behavior. As I said, the use case of our studies, PX4 logs everything that is gathered from the environment, all the sensor information, all the internal communications between different modules. And the goal is to replicate some of those logged behaviors in the simulation environment as well, very similar to the real world. And we do this by finding some optimal drone or environment configurations. It would be placements of the obstacle. This could be the wind of the simulation environment, which in the real world, there could be some wind, but we don't know really how much or in which direction. So we find the optimal configurations that makes the drone behave the same way and in the same settings. And the next step would be, so after this, the first step, we have a replication of the field test that we had from the real world in the simulation. But can we generate, based on this replicated flight, can we generate more challenging but still very similar scenarios in the simulation? So we can diversify our test scenarios, we can generate more challenging scenarios, and even we can guide the next time that we go to the field, we can know what kind of configurations could be harder for the drone to follow. So we can go and test that specific kind of configuration. So this is by also manipulating the environment and configurations. I will go in more details. To be able to do so, first, we need the tool that lets us do large-scale simulation experiments on the drone. For this, I developed a tool called Aerialist. This can be seen as a test bench for drones based on PX4, and this has different modules. There is a simple test descriptions that comes as input. We define the test that we want to do, and it automatically configures the simulation environments and the drone that we want to test and monitor it throughout the flight. The important thing is that it supports both the simulation environment and the real world. So the same commands could be sent to the real environment, to the real drone in the real environment, and to the simulated version in the simulation environment. And then we can compare if those are how different they are. And if we use it with the simulators, we can also generate a simulation environment based on the configuration that we sent. So placement of the obstacle, configurations of the wind, or so on. And the output could be the logs of the flight. So we have logs of everything that happened during the flight, the inputs, the sensor values, the outputs, the trajectory, and everything. So we can then use this log for post-mortem analysis and see how different these tests are. Specifically, to be able to do some larger scale tests, we Dockerized it and we used it. We deployed it on a Kubernetes cluster, so we can run 10 exact same tests in parallel on the Kubernetes cluster, and then we can take some averages, because always there are some small randomness in the simulations as well. So if we run the test once and we get some trajectory, we cannot really depend on that for the comparison. We need to run it a couple of times, and they take some averages of the trajectories or other values that we want to compare. And the test description that I told you about is a simple configuration file that defines the type of drone that we are testing, the parameters of the software because as I said, this software needs to be able to be used with a lot of different hardware and mechanical parts. So there are a lot of parameters to set, and some configuration flows, and also the definitions of the simulation environment, the type of simulator, the obstacles that we want to set, the wind condition, and how we run it, like in Docker or in Kubernetes, and how many repetitions of it we want, and what commands we want to send at runtime to the drone. Having this toolkit helps us to run the experiments that we need for the study. And to give you a short demo of the work. So this is the tool running the replaying a previously logged flight in the simulation. It gets the logs of the real-world flight as input, and it extracts the commands from it and schedules the command to be sent exactly at the same timestamps to the drone. Drone starts to fly with the commands, simple maneuvers, and getting back. Okay, so having this tool, I started to do the study. For the study, first I need a real-world log. So around our campus in Zurich, I found some places that were good enough for the test that we wanted to do. And luckily, I found some obstacles in the almost empty parking lot. So I took advantage of this good timing and automated did an autonomous flight with the drone that we had. So the mission was flying from this spot here to this spot, but there were some obstacles here in the map. So the drone should go around the obstacles and act safely. Interesting thing was that the autopilot around the obstacle was very cautious. It lowered the speed, but as soon as it was free from the obstacle, it really speed up and landed at the landing point. And this was the trajectory that we got from the test. So we have two research questions. The first, as I said, is the first step, and the first research question is flight replication. Specifically, with the log that we saw, with the flight that we saw, can we find the configurations of the environment? Here we just include the obstacle configurations, the size and the position of the obstacle. Can we find can we place an obstacle in the simulation environment to faithfully replicate a real-world autonomous flight trajectory? So the goal is to replicate the trajectory, and by placing the obstacle as in an optimal position. And then can we generate more challenging scenarios based on the replicated version of the real flight? So can we? Here in the study, for making the test more challenging, we thought of just adding a very similar obstacle to the environment. So instead of the one obstacle that we found in the first phase, we add another obstacle to the environment with the same size, and we just change the position. And then we see if we can make it harder for the drone to follow the path. Specifically, can we force the drone to violate the safety distance to the obstacles by placing an additional obstacle in the map? So we developed an iterative algorithm to find the position of the obstacle. We start with the initial position and size for the obstacle. So specifically for the log that we saw before, the blue line is the real world trajectory, and the red one is the average of 5 runs of the test with this specific obstacle that we put in the simulation. And the goal is to make these 2 lines match on each other during the process. So we start with the initial 3.3.3.3 box, and we evaluate in simulation. With evaluation, I mean finding the distance between the 2 trajectories using dynamic time warping, which is a pretty known metric for distance of time series. And then using the mutations that we have, simple mutations like moving the obstacle, resizing the obstacle, and rotating it. And so step by step, we pick a mutation operator. We put the parameters like the delta x, the parameters of the mutation operator, and then we evaluate it in the simulation environment. And step by step, we can get better. We can find better solutions. As you see, we change it up and down, and then we pick the one that is better in terms of the distance, and then continue mutating on the new best solution that we have. And by iterating through this process, step by step, we get better and better solutions until we reach a plateau that we cannot go beyond. So in the end, we were able to push the obstacle at the position and find its size and rotation angle so that the trajectories are almost identical. For the next research question, we took another test case. So here we needed bigger obstacles that were not possible in the real world. The obstacle here are 20 meters high, like a building. And we wanted to see if we can make this. So at the beginning, we didn't have the second obstacle. The trajectory was like this. And we wanted to add a second obstacles and see how the drone behaves when we make the second obstacle closer to the first one, and so on. And we use the same process, but with different distance measure. So the distance measure is trying to force the trajectory to be closer to one of the obstacles and make it a bit unsafer for the drone to follow. Iterating through the same iterative process, we were able to minimize the distance of the obstacle, the drone to the obstacle. Specifically, we were able to make the drone first act non-deterministically, meaning that if we run the same test case, in some of them, the drone would act safely, go round from the left of the first obstacle. In some cases, it will get too close to the obstacle, but not crashing to it. And in some cases, even we saw crashes of the drone to the obstacle. So we found some very specific position for the second obstacle that makes it really hard for the drone to follow. Interestingly, if we make the second obstacle a bit closer to the first obstacle, these lines that you see in the middle, you won't see it. So the drone would always go to the left and be safe during the whole flight. So for the future work, we want to try also optimizing other environment configurations. Here we focus on obstacle position, and size, but we could also check with wind or the ground surface or some more complicated obstacles like trees. Also, replicating the field test with respect to other logged behavior. Here was the trajectory of the drone, what could be motor inputs and so on. And an important thing is that, so we have found here specific obstacle configurations that make it really hard for the simulated drone. But is it really also very hard for the real drone? This is something that we also plan to explore. Okay, so my talk is over. Just a summary. I introduced you to the drone a bit, to its architecture and simulation environment that we have for it, the reality gap that we have when we want to test the drones, and the algorithm that we proposed for replicating test cases in simulation and for generating more challenging test cases based on the replicated version. Okay, thank you very much.